Here we are going to solve some problems and walk through the process of building representation matrices. So in this case here, we have a linear transformation from R2 to R3. So our input space or the domain is R2 and the output space or the codomain is R3. And we have a linear transformation defined here. It takes objects, vectors from R2 and transform them into objects or vectors in R3. And these are the formulas. So our goal is to find first the standard matrix. So the matrix that is relative to the linear transformation, but relative to the basis S standard basis for R2 for inputs and standard basis for the outputs in R3. So how do we do this? Well, we know that each linear transformation is defined by its action on the basis vectors of the input space. So we are going to apply this linear transformation to the basis vectors of R2. So the basis vectors of R2 are 1, 0, 0, 1. So apply the linear transformation to the first basis vector of R2. So we have negative 1. So I'm just going to write it in detail for once. Oops. Okay, so in this case, negative 2, negative 5. So what happened is the linear transformation transformed the input, the basis vector from R2, so this is an object, into another object which is a vector in R3. We know that the vectors in R3 are equal to the vector of their coordinates in the standard basis of R3. Similarly for the vectors in R2, they are equal to their coordinate vector in R2. We know that for the standard basis. It's the same thing. So let's now apply the linear transformation to the second basis vector from R2. And we get as the output an object in R3, which is a vector itself. Nope. This is 3. And this is 6. Oops. Okay, so these are objects in R3. These vectors are equal to their coordinates in standard basis, we know that. So now we have these two pieces to build the standard matrix. Standard matrix is what? T S standard matrix, a standard basis for the inputs, standard basis for the outputs. And we know that these vectors are equal to their coordinates in standard basis. So we put them in correct order. The first image of the first vector and the second image of the second vector. Again, SS. So this is the standard matrix, right? So this matrix, basically when we want to use it, we are going to multiply the vector, its coordinates in standard basis, which is equal to the vector, and then we'll get as a result the coordinates of the image in standard basis, which is actually the image itself. So that's pretty straightforward. So let's have what happens if I take the same linear transformation, but now I'm asked to find the representation matrix T relative to basis B of the inputs and standard basis for the outputs. And basis B is a basis for R2, is given by these two vectors, 3, 1 and 5, 2. So what do we do? Well, it's simple. We proceed as previously. We apply always the linear transformation to the basis vectors. So this is a vector, an object from R2. We apply a linear transformation to it. We're going to get an object, a vector from R3. We remember that linear transformations, they work on objects. In this case, objects are vectors from R2 and R3, right? Representation matrices, they work on coordinates of objects, see? So first thing, we apply T to U1 and then T to U2. So here's the calculation. We apply T to U1, we get this. So we apply T to the object, vector 3, 1. We get, as a result, object vector in R3. Similarly for the vector U2. So these two pieces are the vectors in R3. Now, since we are asked to produce the representation matrix relative to basis B for inputs and standard basis for outputs, we already know that each object in R3 vector is equal to the vector of its coordinates in the standard basis. So we just copy these guys in correct order, right? Image of the first one in the first column, image of the second one in the second column. So we got the representation matrix relative to basis B for inputs and standard basis for outputs. So this matrix, when we use it, B, S, we need to multiply the coordinates of the vector x in basis B. And what we are going to get as a result are the coordinates of the image in standard basis. We know that coordinates of the image in standard basis, vector in standard basis, its coordinates are equal to the vector itself. So in this case, this is what we get. Because coordinates in standard basis are equal to the vector itself. So this representation matrix eats as input or multiplies as input the coordinates of an object in basis B. Okay, nice. Let's make it more complicated. So the same linear transformation. Now what I want is a representation matrix relative to standard basis for inputs and a basis C for the outputs. So basis C is a basis of R3 given by these three vectors here. So what do we do? Well, again, as usual, we apply the linear transformation to the basis of the domain, of the input space. In this case, is the standard basis of R2. So we apply T to the standard basis of R2. We already did this, so we got these two vectors. So these are the vectors in R3. They are equal to their coordinates in standard basis. That's fine, we know that. Now what we want is a representation matrix relative to basis S, standard basis in inputs, and basis C for the outputs, for the codomain. Okay, so what next? So we got the images, which are the vectors, that's fine, but that's not what is asked. They want us to find the coordinates now of these outputs in basis C. So for each of these two guys, we need to find the coordinates of this guy in basis C. And then we need to find the coordinates of this guy in basis C. And then put those results in the representation matrix. Okay. So let's find the coordinates of T10 and T01 and find those coordinates in basis C for R3. So how do we find the coordinates of a vector in a given basis? Well, we need to solve the linear system by Gauss-Jordan. So we just produce an augmented matrix, gigantic one, because we need coordinates for this guy, and the matrix is the same. The first column is the first basis vector, second column is the second, and third column is the third basis vector. Just order them slash the two victims, and then have fun with Gauss-Jordan. Once you finish solving, by the way, there's always a solution. You will get the coordinates of this vector in basis C and coordinates of this vector in basis C. So coordinates of the first guy in basis C are here, and coordinates of the second guy in basis C are here. So the representation matrix relative to basis S for inputs, silent basis for inputs, and basis C for outputs is given here. The first guy goes in the first column, the second guy goes in the second column. That's it. Now we have a representation matrix relative to basis S, C for a linear transformation. So how we use it? Well, this representation matrix multiplies the coordinates in standard basis of an object, and as a result you'll get the coordinates in basis C of the image. So coordinates inputs, coordinates of the outputs, coordinates of the outputs. Okay, be careful. So what we learned is that the same linear transformation has many representation matrices. And all of those matrices are depending on, obviously, linear transformation, but also on the basis for the input space and the basis for the output space. So all of them represent the linear transformation, but relative to different bases for the input space and output space. So be careful about this. It's the same transformation, but different representations, depending on the basis chosen for the inputs and the outputs. In the last part, let's make things a little bit more spicy, and let's find the representation matrix relative to the basis B for inputs and basis C for outputs, the basis that we already saw. So the basis C is for R3, is given here, the previous basis C, and the basis B is this basis for R2, given also previously. So again, the same procedure, we apply the linear transformation to the basis vectors from basis B, do that, we already did this, and then we get the objects from R3. These are the vectors from R3. So that's good. Now, the second step is we need to find the coordinates of these vectors in basis C of R3. So that's the goal. Now, the second step, find the coordinates of each image in basis C from R3. So what do we do? As previously, we put the basis vectors from basis C in the columns, slash, and then we put the images here, and then we find the coordinates by solving the system by Gauss-Jordan. Obviously, there is some work here, and as we see, the result is quite ugly. So the coordinates of the first image are given here in basis C, and coordinates in basis C of the second image are given here. So our representation matrix relative to basis B for inputs and basis C for outputs is given here. We just copy the coordinates in correct order, and that's how we get the representation matrix relative to basis B and C. Again, how this works, this representation matrix relative to basis B for inputs and basis C for outputs works on coordinates, so we need coordinates of vector x in basis B, and then we do the product. What we get out are the coordinates in basis C of the image Tx. So that's how it works. So you see, you give as input the coordinates of x in basis B, and you get as output coordinates in basis C of the image. Ta-da! That's it. So what we learned is that the same linear transformation that we had at the beginning, this one has obviously infinitely many representation matrices, and each matrix is relative to the choice of basis for input space and basis for output space. So the standard representation matrix, where the standard basis is chosen for the inputs and the outputs, is given here, and then the representation matrix BS for the inputs given coordinates of basis B, and the outputs are given in the standard basis. It's given here, we already computed it. We also computed the representation matrix relative to the standard basis for inputs and basis C for the outputs. And lastly, we found the representation matrix of the linear transformation T relative to basis B for inputs and basis C for the outputs. So you see, the same linear transformation has several representation matrices. All of them are different and related to the choice of basis for the domain and basis for the codomain. A last thing, just to make sure we fully understand what's going on. Let's say I have a linear transformation T that goes from R3 to R2. So the domain is R3, so that's the input space, and the codomain is R2, the output space, and I have basis B for R3, given by some vectors V1, V2, V3, and I have a basis C for R2, given by vectors U1 and U2. And then, in this problem, on top of these two bases that are still mysterious, I'm given a representation matrix for this linear transformation T relative to basis B for inputs and basis C for outputs. And it's given here. This is my representation matrix relative to basis B for inputs and basis C for outputs. What does this mean? We need to be able to read this. Previously we were building these matrices step by step. It was straightforward. But now we are going backwards. Just when I see a representation matrix, what does it mean? By definition, this was built as the first column is the coordinates in basis C of the image of V1 by the linear transformation T. So we know that we take T, we apply it to the basis vectors of the input space. So T of V1, we get it, and then we find the coordinates in basis C of R2, and we put it in the first column. Ta-da! Okay, so that's something to remember. This is like understanding what's going on. The second column, so this one here, are the coordinates in basis C of the image of V2 by the linear transformation Vt. Because we would take T applied to V2 and then find, so we get T of V2, and then we find coordinates in basis C. And we put that in the second column. So it's here. And then for the third column, we take the third basis vector from basis B, we apply T to it, and then we find the coordinates in basis C. That's the meaning of it. So when you have a representation matrix relative to basis BC, what this means is that the first column are the coordinates in basis C of the image of the first basis vector in basis B. Second column are the coordinates in basis C of the image of the second basis vector in basis B. And the third column are the coordinates in basis C of the image of the third basis vector in the basis B. That's the meaning. Which means now that this guy is equal to this. So coordinates in basis C of TV1 are these coordinates. What does this mean? By the definition of coordinates, what does it mean? It means that this thing represents 1 times the first basis vector. We have basis vectors u1 and u2 in basis C. So it's 1 times the first basis vector from basis C plus 2 times the second. Up. That's what it is. So we have those vectors eventually, and we are going to be able to compute this and get an answer here. So this answer will be a vector that is the image of V1 under the action of linear transformation T. Second column is equal to this. So the coordinates in basis C of the image of V2 under the action of linear transformation T are these two coordinates. So what does it mean by the definition of the coordinates? It means that TV2 is minus 1 times the first basis vector, minus 4 times the second. So basis vectors from the basis C, obviously. And for the third guy, similarly, we have coordinates in basis C, 3 and 5. So TV3 is 3 times the first basis vector plus 5 times the second. So that's the meaning of it. When you have a representation matrix given to you with the basis, obviously, that's the meaning of it. The first column are the coordinates in basis C of the image of the first basis vector in basis B. So you need to be able to go backwards also. We are able to build this doing this process, but now we are also able to go backwards and understand what this means. So that's an important detail, and you need to be aware of that. So it's not complicated, but you need to be aware of what you're doing. When you're building representation matrix, you need to be able also to make an interpretation when you see it. What does it mean? So that's all about it. It's not complicated, it's quite easy, straightforward, but you need to be awake when you're doing it. A couple of practice problems will help in all this.